Good afternoon, all of you. My name is Nitin Tomar, and I am a fourth year PhD student in the Department of Mathematics. In today's lecture, we'll learn some indirect method. In the past few lectures, we have already talked about Gauss-Seidel method and Jacobi methods. These indirect methods help us in solving a system of linear equation, unlike the direct methods. These methods are also called iterative methods. Now, there were certain conditions that we have seen already to obtain the convergence in these iterative methods. For example, if the matrix A in the system of equation Ax equal to B is a strictly diagonally dominant matrix, and in the last class we discussed certain linear algebra that is required for this lecture. So we start with today's lecture, and we started with an eigenvalue problems. So eigenvalue problems. So what is an eigenvalue first of all? Let A be an n cross n matrix with real entries. As we are already taking in this course, A is always a square matrix whose entries are coming from the real numbers. Now eigenvalues of A are defined as the roots of the characteristic equation, which is given by determinant of A minus lambda I is 0, and this is called characteristic equation. So eigenvalues are nothing but the roots of the characteristic equation. Now why are we studying this? Because we will see a method known as power methods which uses this eigenvalue. So a few remarks before starting. Eigenvalues of A need not be real. Eigenvalues of A need not be real. Even if A has real entries, for example, if you choose your A to be 0 1 minus 1 0, then this characteristic equation determinant of A minus lambda I, this is basically determinant of minus lambda 1 and minus 1. So its determinant will be lambda square plus 1, and we know so this obviously this shows that determinant of A minus lambda I is 0 has no real solution, right? Because lambda square plus 1 it cannot be 0 for any real number. Okay, has no real has no real solution. No real solution. Second remark, for every matrix there are n eigenvalues lambda 1, lambda 2 up to lambda n counted with multiplicity. What does it mean? That if eigenvalue repeats, then we are counting them as many times as they are being repeated. Okay. Now, how do we obtain eigenvalues? See, one obvious way of approximating an eigenvalue of a matrix is to first obtain the characteristic polynomial explicitly in terms of lambda, and then use one of the numerical methods which we'll discuss to compute the root of the polynomial. So computing the root of the polynomial we'll also discuss in the next few sessions, but this is not an efficient way of computing eigenvalues because of two reasons. One reason, that the dimension of the matrix could be very large, and secondly, the roots of polynomials are extremely sensitive to perturbation in the coefficients. So this is an important remark, and we will write okay. The roots of polynomials are extremely sensitive to perturbations in the coefficients. Now we'll show this via one example. Okay, so so this remark is followed by this example. And this was given by Wilkinson. This is due to Wilkinson. So let us discuss this example. Let fx be x minus 1, x minus 2 up to x minus 10, and gx be x power 10. Now both are polynomials of degree 10. Okay, these two are polynomials of degree 10. Am I correct? So these are both are polynomial of degree 10. Now, first thing first, the roots of fx are actually 1, 2 up to 10, and all these roots are simple. By simple root we mean multiplicity 1. Okay, all these roots are simple. Now let's say we do some perturbation and define fx to be, let's say, fx plus 0.01x power 10. Okay, and that is precisely 0.01 times gx. Then one can see that the roots of this polynomial fx, this lie in this interval 1 comma 3.5. In fact, the largest root of fx, as we know, is 10. Is 10, whereas the largest root of this polynomial fx is approximately 3.39 approximately. See, and what does it show? So basically it shows that if the coefficient of x power 10 is perturbed by a small amount of 0.01. So see, this was a very small amount, right? Small amount of 0.01. But the highest root, it's experiencing a very huge difference. Okay, so the root 10 of fx could move as much a distance as 6.6 approximately, right? So hence the roots of polynomials are extremely sensitive to any perturbation. So you just cannot make any perturbation and expect that you still will be in the vicinity of the roots of the polynomial. So this example shows that. Now let us come to the power method. So for that we need first we need a definition. Definition is dominant eigenvalue of a matrix So how do we define it? An eigenvalue lambda of an n cross n matrix A is said to be a dominant eigenvalue of A if this eigenvalue is the maximum among all the eigenvalues, maximum mod mu, such that mu is an eigenvalue of A. Mu is an eigenvalue of A. Okay. So for example, if I give you, let's say 1 minus 2 3 1 3 0, let's say, so we know the eigenvalues will be the diagonal entries. So the eigenvalues of A are 1 and minus 2, and the dominant eigenvalue is minus 2, right? So this is first example. There can be more than 2 dominant eigenvalue. For example, you take B to be, let's say, 1 and minus 1. Let's say again you take 3, or maybe let's say take 1. Then what are the eigenvalues? So the eigenvalues of B are 1 and minus 1. Both are dominant eigenvalues. Both are so it is not necessary that a dominant eigenvalue will be unique. So that is why we wrote a dominant eigenvalue, not the dominant eigenvalue. Okay, here we have written a, not the. Yeah. Okay, so few remark. Yeah, and these are easy remarks. Let's say if a dominant eigenvalue of a matrix A is 0, then all its eigenvalues is 0, right? Then all its eigenvalues are 0. Then all its eigenvalues are 0. Also, any eigenvector is a non-zero solution of Ax is 0. And why will such a non-zero solution be existing? Because see, A has an eigenvalue 0, which means A is not invertible. So hence this system Ax equal to 0 will have a non-zero solution. We have already seen in the beginning that Ax equal to 0 has a 0 solution if and only if A is invertible. Now since in this case, since A is not invertible, so there will be a non-zero solution, and the non-zero solution will be indeed an eigenvector. Second, let's say if lambda is a dominant eigenvalue, of a matrix A, then there is no other eigenvalue of A whose distance from 0 is greater than that of lambda from 0. And this is nothing, just language, okay? Like distance of lambda from 0, what it is actually? It is just mod lambda, right? This distance is actually mod lambda. And distance of eigenvalue from 0, this, let me use another pen. So if we are considering this distance of eigenvalue, then it will be some mod mu. So, and because lambda is dominant, so what does it mean? Mod lambda will be greater than equal to mod mu. So this is precisely what it means. See, the eigenvalues of A can be arranged as in this manner, right? And this is precisely the dominant eigenvalue, This is a dominant eigenvalue. See, nowhere in the definition we are claiming the dominant eigenvalue. We are always saying a dominant eigenvalue, okay? Now, okay, so now we move towards the power method. Okay, let us do some more examples. Okay, let's say first, let's say this AB 1 0 0 0 minus 2 0 0 1 and minus 1. Now clearly this has eigenvalues because it is an upper triangular matrix, so it has eigenvalue 1 2 minus 1 1 minus 2 minus 1. In this case, the matrix A has unique dominant eigenvalue and what is it? It is minus 2. Second, if you take B to be 1 2 minus 2 3 4 1, just a minute. Yeah. So if you consider this matrix, Now you see this has eigenvalues. What are the eigenvalues? 1, 2, minus 2, and dominant eigenvalues are 2 and minus 2. So there is no unique eigenvalue. Okay. So there are two eigenvalues. There is unique dominant eigenvalue. Now in third case, yeah, so now let us move towards the power method. So the aim of the power method is to compute the number 1 dominant eigenvalue, number 2 the corresponding eigenvector of matrix A. So these are the two aims. So let us learn the power method in detail. Hypothesis for power method. So we assume certain things. Hypothesis for the power method. Now assume that an n cross n matrix A has real eigenvalues lambda 1, lambda 2, lambda n. Now these are repeated up to their algebraic multiplicity. As per their algebraic multiplicities such that the following holds. So number 1, so this is hypothesis 1, let us call it H1. A has a unique dominant eigenvalue. A has a unique dominant eigenvalue. So this is the first assumption. So you can write the eigenvalues of A. So that is, we can write the eigenvalues in this way. This lambda 1, you see here you have only strict inequality. So this is actually the unique dominant eigenvalue. Unique dominant eigenvalue. Now, second hypothesis is eigenvectors of A forms a basis for Rn. Forms a basis for Rn. So what does it mean? This is really important. What does it mean? It means, so that is, there exists vectors v1, v2 up to vn such that a v1 is lambda 1 v1, a v2 is lambda 2 v2, and a vn is actually lambda n vn. And this set v1, v2, vn forms a basis for Rn. All this katha, all this story can be put into one line. This is same as saying A is diagonalizable. A is diagonalizable. Now the third assumption is an initial guess See, what we need to do, we need to find, given a dominant eigenvalue, we need to find an eigenvector. So we start with an initial guess. See, this is an initial guess for the eigenvector corresponding to the dominant eigenvalue. So it should be chosen such that, now because you see x naught, it can be written as this Cj Vj, j going from 1 to n, and this C1, C2, Cn, all this belongs to R, and C1 is non-zero. It should be chosen in this way, and this x0, it does not belong to any kernel of AK, k going from 1 to a. So it does not belong to this union. Now what does this line mean? So this precisely means this. AKX0 is not 0 for all k equal to 1, 2 and so on and so forth. Because if for some k AKX naught is 0, then it will belong, x naught will belong to kernel AK and hence in the union, which we don't want. Okay? Yeah. So there are three hypotheses. First, unique dominant eigenvalue. Second, A must be diagonalizable. And third, the initial guess should not belong to the union of kernel of powers of A. Okay? Yeah. Now let us discuss the key idea. The key idea behind power method. step 1. So step 1, first you start with an initial vector. You start with an initial vector x naught in Rn. Arbitrarily, so that we can find scalars C1, C2 up to Cn in R such that x naught is actually C1 V1 plus C2 V2 and up to Cn Vn such that this factor is non-zero. This is non-zero, so this should, I am highlighting this. This is not zero. Now step 2, if you multiply this by a, it will be C1 a V1. Okay, let me just write. Pre-multiply both sides with a. Then you will get something like this: C2 AV2 and so on so forth. See why this will be true? See, because now V1, V2, Vn, so these were eigenvectors, right? So they will be C1 lambda 1 V1 plus C2 lambda 2 V2 plus Cn lambda n Vn. Now if you take lambda 1 common, you can take that because lambda 1 is non-zero, so you can divide and multiply. You will get C1 V1 plus C2 lambda 2 by lambda 1 V2 So what we are trying to do here is the following. We have just divided and multiplied both numerator and denominator by lambda 1, or in other words, we have taken lambda 1 to be common. Now see, because lambda 1 is strictly, because see, in one of the assumption, you see, here you had this inequality, right? So it automatically means, this implies mod lambda 1 is strictly greater than 0. Okay? So lambda 1 cannot be 0. So this taking lambda 1 in the denominator is well defined. So lambda 1 is non-zero and this follows from H1. Hypothesis 1. So this is where the first hypothesis has come into the picture. Now step 3. Again you multiply it by A. Okay, so again you pre-multiply both sides by a, and you will get a square x naught as, it will be lambda 1 as it is, then c1 av1, then c2 lambda 2 by lambda 1 v2, then cn lambda n lambda 1 avn. I think I forgot a here. Yeah. Now if you compute this, so this will be c1 lambda 1 v1, then c2 lambda 2 v2, and cn lambda n lambda 1 again lambda n vn. So again if you take lambda 1 square common, so you will get something like this. I am just copy pasting, it is easier here. So you will get square, square and square, right? Now you keep on doing this. The idea is to keep on doing this. So repeat this process k times to get the following. You will get that a power k x naught is actually equal to lambda 1 k, this is power k and this power k. Now you see this, let this be step 4. Now since lambda 1 is strictly greater than all other lambda j for all j 2, 3 up to n, so this implies mod of lambda j by lambda 1 is strictly less than 1 for all j n from 2 to n. Yes, so this implies limit lambda j lambda 1 power k as k goes to infinity is 0 for all j varying from 2, 3 up to n. So hence if you take limit a k x naught as k going from infinity, it will be upon में lambda 1 k, it will be same as limit k going from infinity Let me just put it into a better frame. Yeah, I think this is the best I can do. Yeah, so you just so it will be k, then it will be k, then vn. So everything will go to 0 and it will just be your c1 v1, right? Now, and since c1 is non-zero, and v1 is an eigenvector, v1 is an eigenvector for A, and it was corresponding to lambda 1, remember, which was the dominant eigenvalue. Dominant eigenvalue. So this implies this vector c1 v1 is also an eigenvector of A corresponding to the dominant eigenvalue of A. So in this way we have already obtained an eigenvector corresponding to the dominant eigenvalue, and this was one of our aim, right? So the key idea says, okay, this is fine, that we can definitely do this. Now, how to find the dominant eigenvalue? So this step is to find the dominant eigenvector. Okay. Now let us go to step 5th, which helps us in finding the dominant eigenvalue. Dominant eigenvalue. And how do you do it? So clearly, if we just take this limit ak plus 1 x naught upon limit ak x0, if you divide it, so what are you getting? You check that, definitely we will be getting lambda 1. Okay. Yeah, and like you just see, the problem will be when this can be 0, so we just take any I where I is any index such that the fractions on the left hand side are meaningful, and this is possible when the denominator is non-zero, and that is when x naught does not belong to union of kernel AK, right? And this is where the third hypothesis comes into the picture, and this holds due to H3. So when you find this limit, it will be lambda 1. Yeah. So we have seen, yeah. So remark, the power method generates two sequences, Number one is this sequence AK plus 1 x naught by AK x naught with some with some index I. You just take any index, okay, let us prove actually why does it converge to lambda 1, otherwise there might be some confusion. So it will be lambda k plus 1, then c1 v1 plus summation cj lambda j by lambda 1 k plus 1 v2 vj, right? J going from 2 to n. Now this is a vector, right? So it does not make any sense dividing by vector. So that is why we take any index, because this is a vector, so we take any index. Ith entry, it means ith entry of vector AK x naught. Okay, this precisely means this. No, it's ith entry. It's ith entry also. Now you see, this is just lambda and it will go to, okay, let me rejoin. Yeah. So this will go to So this is lambda 1, and this will go to c1 v1 I and then c1 v1 I, right? So you just choose I such that ith entry of c1 v1 is non-zero, and this will be true because c1 v1 is a non-zero vector. So then it will be lambda 1 as k goes to infinity. And another sequence is this sequence, right? And the second sequence is this, which goes to v1. So we have two sequences. First, it converges to the dominant eigenvalue, and once we have the dominant eigenvalue lambda 1, using that we have another sequence which goes to the eigenvector corresponding to the dominant eigenvalue. Okay. So let us see the steps involved in the power method. So we now describe the power method iterative sequences. So step 1. Step 1 is choose a vector x0 arbitrarily large. You just choose any vector and set y1 as ax0 step 2, define mu1 to be yi1, where this I, see there is this some I, right? This I, where this I belongs to 1, 2 up to n. It is the least index such that the subnorm of the vector y1 is attained at this index. Okay, and then set x1 to be this y1 upon mu1. Okay, now mu1 why it will be non-zero? Mu1 will be non-zero. Why? See, mu1 was this index I Mu1 is yi of 1, where I is the index where this y attains its the supremum value, the modulus of the coordinate. Now if this is 0, let's say mu1 is 0, which means y1 supnom is 0, and this is possible if and only y1 is 0, and this means ax0 is 0, which means 0 is in, we are starting with the 0 as an eigenvalue, but we'll see that it is not possible. Yeah. Step 3. Now step 3 is to repeat this process again. From x1 now you obtain mu2 and x power 2 as in step 2. As in step 2. Now repeat this procedure. Okay. So we write down the general form. General form of the power method iterative sequences. So we just give the general form, then we'll go to the examples and we'll see what have we there. So as we have seen already in the key idea, we need to have two sequences, one which will converge to the dominant eigenvalue and second which will converge to the eigenvector corresponding to the dominant eigenvalue. So after choosing the initial vector x naught, arbitrarily we generate the sequences mu k and x power k using these formulas, using the formulas mu k plus 1 as this, and 1 xk plus 1 will be generated by this, and you'll have this. So these are the general form where this yk plus 1 same is, we define it to be a of xk, and I is such that mod of yi k plus 1 mod. This is actually norm of yk plus 1 infinity. So for k going from 0, 1 up to so on and so forth. So this is precisely the general form. Now this iterative procedure is called the power method. So we'll see examples sooner. A quick remark. We have a scaling factor introduced. The scaling factor mu k makes sure that x power k has its maximum norm equal to 1. That is, and it makes a lot of calculation simpler. So this is the first remark. Second, this rules out, when this iteration xk has norm 1, then it rules out the possibility that limit xk being 0, or rather I should say 0 or infinity. So it cannot happen because the scaling factor that we have introduced ensures this. Okay. So let's revise so far what we have done. So the aim of today's session has been so far to find the eigenvalues, and in particular the maximum eigenvalues among all the eigenvalues in terms of its modulus. So to start with, we saw what is an eigenvalue. An eigenvalue is nothing but a solution of the characteristic equation given by determinant of a minus lambda I is 0. We saw that eigenvalues need not be real even if A has real entries, and for every matrix A there are n eigenvalues, and these eigenvalues can be very well a complex number. Then we saw that the roots of this characteristic equation, in particular the roots of polynomials, in particular these characteristic equations, are extremely sensitive to perturbations in the coefficients. So for example, this example is due to Wilkinson, which shows this phenomena. What you do, you just choose your fx to be x minus 1, x minus 2, x minus 10. So this is a degree 10 polynomial with simple roots 1, 2, 10. And again, you choose another degree 10 polynomial with just x power 10. Now if you perturb fx, what is the coefficient of x power 10 in fx? It is just 1, right? So you just perturb the coefficient of x power 10 in fx by 0.01. So that is, you define a new polynomial fx as capital Fx is small fx plus 0.01 gx. We saw that even with this perturbation, the roots were at very great distance. For example, the largest root of small fx is 10 and the largest root of capital Fx is 3.39, which are very far apart. So this shows that the roots of polynomial behave badly even when you add a very small perturbation in the coefficients. Now, with this in mind, we come to the power method. So the power method is a method to find the dominant eigenvalue of a matrix and the eigenvector corresponding to it. Now what is a dominant eigenvalue? An eigenvalue, we know what is an eigenvalue. Now the dominant eigenvalue is the is an eigenvalue among all the eigenvalues which has the maximum modulus. Now, nowhere we are claiming that the dominant eigenvalue will be unique. It can have the dominant eigenvalue. All eigenvalues can be dominant eigenvalues also. So we saw some examples with this. Now, if a dominant eigenvalue is 0, for example, in this remark we saw that, then each eigenvalue has to be 0 because the dominant eigenvalue is 0. Secondly, if lambda is a dominant eigenvalue of a matrix A, then all other eigenvalues will have distance from 0 not greater than that of lambda from 0. This is just some fancy language used here, but it follows from the definition because the distance of a point from 0 is nothing but the modulus of that point. Now, secondly, with this concept in mind, we can arrange the eigenvalues as in the decreasing order, and the first eigenvalue will be a dominant eigenvalue. Now, again, some examples we saw to realize that there can be a unique dominant eigenvalue. There can be cases when we have a unique dominant eigenvalue, and there will be some cases where dominant eigenvalue is not unique. Now, with this in mind, we started with power method, and the aim of the power method is to compute the dominant eigenvalue and the corresponding eigenvector of A. So what is a power method? So any method starts with certain assumptions, certain hypotheses. So the power method starts with 3 hypotheses. So the first is this, that A only has one dominant eigenvalue. So that is, there is a unique dominant eigenvalue. Secondly, A is diagonalizable. That is, eigenvectors of A form a basis for Rn. And the third assumption is that your initial guess should not be in any kernel of A power k. If it is, then we will have some problem, and we'll see where are these 3 assumptions used in the key idea. Now, with these 3 assumptions in mind, we move to the key idea behind the power method. So, because see, the first thing you use, this is due to H2. Yes, this is due to H2. Yeah, I just forgot to write. Step 1 is due to H2. Because we have assumed the eigenvectors form a basis of Rn, so which means you take any initial vector, it can be written as a linear combination of v1, v2, vn with the first coefficient c1 being non-zero. And if you multiply it with A, then you will get step 2. Again you multiply step 2 with A, you will have this thing, and you continue doing so. So we saw that we will get 2 sequences, one which will converge to the dominant eigenvalue, and second a sequence of vectors which converges to an eigenvector corresponding to the dominant eigenvalue, right? Yeah. So the aim is to construct these. So the aim, now that we know the key idea behind the power method, the aim is to construct these 2 iterative sequences. So how do you start? You start with any arbitrary initial guess and set your first iteration to be just AX0. Now you take mu1 to be the component of y1 where it attains its supremum norm, and you choose I to be the least such indices. Then you define your first iteration as x1 as y1 which was already ax0 and upon mu1. Okay. Now you should realize that this mu1 has to be non-zero. Okay. Why? Because see, if you take mu1 to be 0, then it does not make any sense. If mu1 is 0, then yi1 is 0, which was the point where the supremum was attained. So this y1 will be 0, which implies ax0 will be 0. So you may not, and We do not want to start with an eigenvector with an initial guess where it will give us 0, because we want to find an eigenvector, so everything has to be non-zero here, and you continue this process. So we have a general form for the power method iterative sequence, which looks horribly mathematical, but it is what it is, and if you follow it, this comes very naturally. Okay, yeah. So now let us see a theorem. So theorem, now this theorem is a convergence theorem for power method. A convergence theorem for power method. So let A be an n cross n matrix with real eigenvalues such that the all those three assumptions that we have seen, they hold. Okay, so I'm just going to copy those three assumptions from there. Such that these three assumptions hold, such that the following properties hold. What are these three properties? Yes, these assumptions, right, that we have seen. So with this, we have a conclusion. So conclusion number 1. We have already seen why. This sequence, where is this sequence? Yeah. So this sequence then this holds. First thing, first conclusion is this. So this is the first conclusion. And the second conclusion is where is this sequence. So this sequence converges to an eigenvector corresponding to the eigenvalue lambda 1. Okay, let us see its proof. Though we have already mentioned the idea of the proof, but quickly let us prove it. So we call this sequence to be mu k. Okay, and we call this sequence to be xk. Yeah. So from the definition, now you see what is the definition of xk. From the definition of xk plus 1, we must have this x superscript k plus 1. It should be mk plus 1 a power k plus 1 x naught, where this mk plus 1 is actually mu 1, mu 2, mu k plus 1 inverse. But you see, because we could write our initial guess in the form of c1 v1 plus cn vn, where our c1 is non-zero. So thus I can actually write xk plus 1 as mk plus 1 lambda 1 k plus 1 times c1 v1. Yes, we have already discussed this in the above, so I am just writing step by step. Lambda j by lambda 1 k plus 1 vj, j going from 2 to infinity, 2 to n, now if you take maximum on both sides, taking maximum norm on both sides and noting that, so just take maximum note on both sides and note that the way we have chosen xk infinity is 1, the supreme norm of xk is 1. This follows from the adjusting factor mu we get. We have already mentioned why this norm is 1 in the remark. We get this, that 1 is actually mod k plus 1 lambda 1 k plus 1 mod times norm of c1 v1 j going from 1 to n cj then this will happen, right? Okay, I have to, I think, rejoin. Yeah. So we'll have this as the norm. Now, since lambda j by lambda 1 mod k, this goes to 0 as k goes to infinity, we get k going from infinity this will be actually 1 upon norm of c1 v1 infinity, and because c1 is a non-zero scalar, I can actually pull it out, and we'll get this, and this is obviously less than infinity, right? So using this, we get limit k going from infinity, this xk plus 1, we know it is limit k going from 1 to infinity, k to infinity. This is the definition. So it is either this will be either this, either plus or minus, or it oscillates between these two vectors. It oscillates between these two vectors. So what does it mean? It means it will have two subsequent, every subsequence either converge to v1 this plus v1 upon supremum norm of v1 or minus v1 upon supremum norm of v1. In either case you just consider that subsequence and you will have that this, so this completes the proof in conclusion 2, because you can always choose subsequence that will converge to either v1 upon v1 norm infinity or minus v1 by norm infinity of v1, and in either case you are getting a scalar multiple of v1, and remember v1 was already an eigenvector corresponding to the dominant eigenvalue. So in either case you are getting an eigenvector corresponding to the dominant eigenvalue. Okay, yeah, so this proves in that sense the conclusion of this completes the proof of conclusion 2. So this is done. Now we have to prove the sequence part, and the sequence part we have already proved, but let us just repeat those arguments. Now let us show that, or better to write to show mu k converges to lambda 1 as k goes to infinity. So note that this limit yk plus 1, you follow the definition and it will be k lambda 1 v1 up to a subsequence where this k is actually plus minus 1 by norm v infinity. Now since v1 is an eigenvector, there is at least one non-zero component. See, all this argument I have explained above very theoretically. Now we are just writing it mathematically. Non-zero component of v1. Now we choose one such component, right? Because if there is one non-zero, we just need that much. So we choose one such component of v1 and denote it by v1j. Okay. Now again, since v1j is non-zero, and yjk plus 1, this converges to k lambda 1 v1j as k goes to infinity. Now what does it mean? It means that as k goes to infinity, so it precisely means that there is an integer capital N, positive integer capital N, such that yj k plus 1 is non-zero, or rather I can write it as, okay, anyway this will be non-zero after a certain stage, because if no such stage exists, which means this is a 0, because this is non-zero. See, similarly, using all this jargon that we have developed for yjk plus 1, similarly we can say that xjk plus 1 is actually non-zero for all k greater than equal to n. So therefore we can write mu k plus 1 as yjk plus 1 upon xjk plus 1, and this is same as saying axkj upon xk plus 1j, where j is the index, where j denotes the component as above. We have chosen j such that v1j is non-zero. Okay, so this is that same index we are working throughout. Now taking limit, we know that this limit will actually go to lambda 1, and the proof is complete. The proof is complete. So in the conclusion, we should write a subsequence. Yeah. Because we have got a subsequence. A subsequence of xk. Yeah, so a quick remark, then we'll revise the proof. The above theorem does not guarantee the convergence of the sequence itself, right? It guarantees the convergence of one of its subsequence. So it does not guarantee the convergence of the sequence itself to an eigenvector corresponding to the dominant eigenvalue corresponding to the dominant eigenvalue, but rather a subsequence. Okay, this see, okay, here you just see we have in the conclusion that a subsequence of xk converges. We are not saying the sequence itself converges. Okay, so that is some difference, that is some precaution that one has to be taken, one has to take care of. But rather, if we assume certain extra condition, then we'll have this sequence will indeed converge. So this is called second convergence theorem for power method. Second convergence theorem for the power method. Yeah. So yeah. So what does this theorem say? It says let A be an n cross n matrix satisfying the hypothesis H1, H2 and H3 of the above theorem So this is the above theorem. In addition, we have another hypothesis. We will call it H4. And what does it say? Let V to be V11, V12, be such that there is a unique index J belonging to this with the property that V1J is actually same as this. So this hypothesis is called as that the vector V1 has a single maximal component, because we want a unique index J, okay? Single maximal component. So for example, first hypothesis is unique dominant eigenvalue, second is diagonalizability of A, and third is the initial vector should not belong to any kernel of AK. Single maximal component. So then the conclusion will be number 1, the sequence mu k converges to the, so this conclusion is same, right? This conclusion does not change, converges to the dominant eigenvalue lambda 1. But the second conclusion is the sequence of vectors. Now we are not saying the subsequence, we are saying the sequence itself, okay? The sequence of vectors x power k, not power k, it's just x superscript a, converges to an eigenvector corresponding to the dominant eigenvalue lambda 1. So the proof is not actually very difficult, okay? We will see the proof maybe, but you should notice the difference between the first theorem and the second theorem. With the additional hypothesis H4, we get that actually the sequence of xk itself, this will converge to an eigenvector corresponding to the dominant eigenvalue lambda 1, okay? So with this we see the drawbacks of power method. So drawbacks of the power method, because we know any method, any numerical method, it will have some disadvantage. And power method in itself, because it is based on the four additional hypotheses, it might have many drawbacks. First is first drawback is the power method requires at the beginning itself, that the matrix has only one dominant eigenvalue. But see, this is the aim of the power method, right? To give us the dominant eigenvalue. So how can we say it has only one eigenvalue and at the same time we want to compute? See, if you want to compute, this means you do not know about the dominant eigenvalue. But power method requires this information to be available. So this information is generally unavailable. So see, very first hypothesis is very explicitly unavailable. The idea is, it's pretty simple, right? See, what do we want to say here? The very first hypothesis of power method. Okay, let's go back to the very first hypothesis. What does it say? That the matrix A must have a unique dominant eigenvalue. And what is the aim of the power method actually? To give us the dominant eigenvalue, to give us a dominant eigenvalue. So how do we know a matrix will have a unique dominant eigenvalue if we are wanting to compute it? See, that is the point of computing a certain thing, that we do not know anything about it, right? So this is kind of a paradoxical situation. So this information is generally unavailable. So that is the first non-trivial thing, and it is a drawback. And second is, even, okay, let's say this information is available, okay, even when there is only one dominant eigenvalue, it is not clear how to choose the initial guess, right? How to choose the initial guess x0 such that it has a non-zero component C1 as per the notation of the theorem, right? We use C1 as per the notation along the eigenvector V1. See, the second drawback is, how do we choose initial guess such that it has a non-zero coefficient along with V1? See, again, this is paradoxical in the sense we want to ensure that the coordinate of x0 in along v1 is non-zero, but v1 we also want to compute, because v1 it is an eigenvector corresponding to a dominant eigenvalue. So if we already know, you know I hope we want to compute a dominant eigenvector, but the hypothesis also involves certain condition involving dominant eigenvector. So what all in all what we want to say here is that the hypothesis of power method involves, let us go back to the hypothesis part. Yeah. So the hypothesis of the power method involves certain restriction on dominant eigenvalue and dominant eigenvector which are to be constructed. So we are assuming certain things about certain assumptions we are making about things we need to compute, things we want to attain via this method. And hence in this sense this power method is very restrictive. It is generally these kind of informations are not available. Okay. So maybe in the next session we will see uh, all these three cases one by one. When does it happen? Okay. And there is a certain theorem called inverse power method which we will see. So yeah, so there are certain things that needs to be done along these lines of aim in our mind to compute a dominant eigenvalue and to compute an eigenvector corresponding to the dominant eigenvalue. So okay, let us see what we have done today. Today's session started with discussing what do we mean by eigenvalue and what do we mean by characteristic equation. So eigenvalue problem. So square matrix, for a square matrix eigenvalues are nothing but the roots of the characteristic equation given by determinant of a minus lambda I. You solve this equation and you will get your eigenvalues. Eigenvalues, as we have seen, it need not be real even if A is a matrix with real entries. For example, this 2 cross 2 matrix 0, minus 1, 1, 0. We saw its characteristic polynomial is lambda square plus 1, and this shows that determinant of A minus lambda I can never be 0 for any real solution. And also for every matrix there are n eigenvalues, lambda 1, lambda 2 up to lambda n, counted with multiplicity. What do we mean by counted with multiplicity? It means if you have repeated eigenvalues, let's say 0, 0, 1, then we'll count them as 2 and plus 1, okay, 3. Now see, because characteristic equation is a polynomial, so it is important to study the roots of polynomials under perturbation, and this is due to Wilkinson. So this remark says that the roots of polynomials are extremely sensitive to perturbations in the coefficients, and we have an example due to Wilkinson, and this says that you just take these two function polynomial fx as x minus 1 times x minus 2 times x minus 10. It is a degree 10 polynomial, and you take gx to be x power 10. Then the roots of fx are 1, 2, up to 10, and all these roots are simple roots. And you perturb this polynomial fx by adding 0.01 in the coefficient of x power 10, which is precisely fx plus 0.01 gx. So the roots of fx lie in 1, 3.5. And if you try to compute, the largest root of fx is 10, which is clearly obvious, whereas the largest root of fx cannot go beyond 3.5, right? So thus if the coefficient of x power 10 is perturbed by small amount of 0.01, you see the roots are at a great distance, right? So in this way the roots of polynomials are extremely sensitive to perturbations in the coefficients. Now with this theory, with this much of background, okay, just a minute, I need to share my screen again. Just a minute. I'm joining. Somehow this share screen. Yeah. Yes. Oh, yes. Yeah, I think now the screen is visible. So then we have this concept of dominant eigenvalue of matrix. We saw that the dominant eigenvalues, it might be unique, it need not be unique. So all these things are there. Then we came to the power method. The aim of the power method is to compute the dominant eigenvalue as well as the corresponding eigenvector. So we have certain hypotheses for the power method. First, A is a square matrix with real entries such that it has a unique dominant eigenvalue. Second, the A must be diagonalizable, that is, its eigenvector should form a basis for Rn. Third, the initial guess should be such that the coefficient along V1, that is C1, should be non-zero. And remember, V1 is an eigenvector corresponding to the dominant eigenvalue. And X naught should not belong to the union of kernel AK. Okay. Now see, with these three hypotheses, you see here comes the drawback. You see, the first hypothesis say, dominant eigenvalue should be unique. But the aim is to compute the dominant eigenvalue itself. So how can we be sure about that there is a unique dominant eigenvalue, whereas we want to compute it? Okay. So this is first drawback of this power method. Second hypothesis has something to do with the dominant eigenvector corresponding to the dominant eigenvalue. It says, third hypothesis, sorry. It says the coefficient of your initial guess, that is C1, which is the coefficient along vector V1, should be non-zero. But V1 is an eigenvector corresponding to the dominant eigenvalue. So how can we be sure? Because V1 is again one vector which needs to be computed. And these hypotheses already involve certain assumptions what we need to compute. So in that sense, it is a major drawback of this method. So none so far. We saw the key idea behind the power method. You just choose any initial vector, non-zero. You just choose any non-zero vector x0. Due to h2, you can write it as a non-zero linear combination of the eigenvectors v1, v2, vn, and c1 should be non-zero. You can choose. Step 2, you pre-multiply it with a. Step 3, again what you have attained in step 2, you pre-multiply it with by a again, and you keep on doing this process, and you see that you will get two sequences, one of which will converge to the dominant eigenvalue, and second you will get a subsequence which will converge to an eigenvector corresponding to a dominant eigenvalue. And this is precisely the first convergence theorem for power method. It says that, with these three assumptions, you have the following conclusion, that you will have a sequence of scalars which will converge to the dominant eigenvalue, and second you will have a subsequence of vectors which will converge to an eigenvector. Okay. Now see, in the second conclusion you have a subsequence, not the sequence itself. So to attain the convergence of the sequence, you have to add additional hypothesis which is known as that V1 has a single maximal component. Okay. And if that happens, then the sequence of xk itself will converge to an eigenvector corresponding to the dominant eigenvalue lambda 1. So there are certain drawbacks as we have discussed. So with this we finish our session. In the next few sessions we will see examples of this power method, and we will see, this power method has at least three hypotheses. We'll see what if we drop each hypothesis and what happens there. So that will be the target. We'll see that if we remove any of the hypothesis, then the power method fails. So if we remove h1, we will have one example. If we remove the hypothesis h1, we will have one example where the power method will fail. Similarly, when you remove hypothesis 2, you will have a counter example where the power method fails, and as for h3 and h4. Okay, so all these things will be there. And secondly, first, before that, we'll see how to apply power method once all the hypotheses are met, and then this removing hypothesis part. Secondly, we will see another version, another better version of it, which is called inverse power series method. There we'll assume that A is invertible, which means all the eigenvalues are non-zero. And after that we'll see this whole idea of these power methods is to find the eigenvalues. So there is certain thing called Grisgor's theorem, and it gives a disk. It gives the union of disks where beyond that no eigenvalues will lie. But we will see that there also. So with this we finish our session. So yes. So this was week 8. If you have any doubt, you can always mail me. I am a 4th year PhD student in the Department of Mathematics at IIT Bombay. You can have my mail address from there, the web page of the IIT Bombay, if you have certain doubts. If not, then it is fine. Okay, then I'll stop sharing my screen.